Namaskar my dear friends. So let us try to see what are the best practices for ADC converter connections. Okay. So we have ADC either in microcontroller, that is inbuilt ADCs, or we have separate ADCs ICs. Okay. So there are a lot of manufacturers like and Texas Instruments, Analog Devices, Maxim Integrated, Linear Technology, and other so many manufacturers are also there. Okay. So what we'll do is we'll try to understand what is ADC reference, what is ADC beats. So ADC reference voltage you already know. Let us say it can be 3 volt, 2.5 volt, 5 volt, or 1 point, like 5 volt or 1.25 volt. Any reference can be set. Okay, either it is internal to the device or external to the device. Similar to that, ADC beats. So bits resolution can be 10 bit, 8 bits, 12 bits, 16 bits. It can go up to 32 bits also, which is very high end ADCs. But we don't need that much. Okay. Now, what is the ADC counting? How it works? If you have 12 bits, then it will be 2 to the power 12 minus 1. It means how much? It is 4096. So the counting will be from 0 to 4096 counts. Okay. Similar to that, 2 to the power 10 minus 1, that is 10 bits ICs, 10 bits ADCs. So it will become 0 to 1023. Similar to that, if it is 16 bits, then it will be 65,535. So this is the range that will be having the ADCs. Okay. All right. With this, let us do little more calculation. If you have, let us say 14-bit ADC, then what will happen? The total number of calculation will be 16,383 units. Okay. Let us say you have a analog input of 1.2 volt and reference voltage of 2.5 volt for the ADC. The corresponding ADC value that will be read by the ADC converter is 7,863. Okay, around that 1 or 2 units up or down it will be because of errors. Okay, understood. Suppose you have a ADC value that you have read in the converter is 1020, then the ADC analog value will be 0.156, or let us say you have read just now 7863, so we'll put that value here, 7863 or 64. Okay, it will be close to 1.2 volt. Okay, so it is coming close to 1.2 volt. Now if you change the reference voltage, let us say 3, then its value will be changed. So it has become 6533. Understood? And corresponding to that, if I am putting 6553, then the corresponding value of analog values will be 1.2 volt. So this was all about ADCs, ADC beats and ADC references, and what is the ADC value for a particular analog inputs and digital outputs. Okay. Now we'll try to understand. Let us say we have a voltage level 12 volt from battery source. Okay, and we want to send it to the ADC. So what are the different circuits that will be making or that will be putting so that it goes directly to the ADC properly. Okay, so first of all we have to understand that the ADC can be from microcontroller. Okay, or it can be an external ADC. Okay, so microcontroller ADC, you have seen lot of microcontrollers. Let us say we have seen PIC 16F or PIC 18F. Okay, we have seen DSP ICs from microchips, all right. Then we have seen Texas Instruments ICs also, like MSP 430 I2041. Okay, that was having 16-bit ICs, 16-bit ADCs. Then we have MSP M0L1105 and 1306. Okay, and similar to that MSP M0Z3507 or 3506. Okay, we have lot of applications with our microcontroller from ST Microelectronics, that is STM32L053. Okay, similar to that STM32Z071 and so many other ICs as well. Okay, we have also seen STM32L433. Okay, so these are the ICs that we have already had the application in our devices. At the same time, we have lot many other manufacturers that we had used in our applications like Renesas ICs or NXP IC, but that's not the thing that we have to worry about. What we have to worry about is, let us say one of the circuit that is there with us. So in this PIC 18F46Q71, this is one of the most advanced IC that is there with PIC microcontrollers. Okay. So almost all the lines are having ADC capabilities except the power pins and ground pins. Okay. So you can see, let us say we have to add one, ADC input to RE0, which is having some ADC. Okay. So what would be the connection directly shall we connect? Let us say we have to attach, a 12 volt, that is the input that we have, and we want to keep it measured, like we want to measure it what is the value of voltage. So for that, can I connect directly or do have to do something else? Okay, so that's what we will learn. So that is the best practices that we will have to follow. Okay, so let us see what are the best practices to make the ADC connection properly. Okay, so in that case, let me just take here. We have a battery voltage input which is close to 12 volt. Okay, so first of all, our aim is to make understand what is my V reference of ADC. Okay, so let us say V reference of ADC is 3 volt. Okay, so our understanding is the analog input that will be going to ADC value must not be more than 3 volt. Okay, it should be lesser than 3 volt, maybe 2.5 volt maximum. Okay, or 2.2 volt maximum, like that. Okay, so for that we will downgrade it by having a resistor division. Understood? So this is the thing what I have done is I have taken 390 kilo ohm and 75 kilo ohm. So in that case, the Vx1 will be coming up how much? 1.93 volt. Okay, if you take 100 kilo ohm, then this will come up as how much? 2.45 volt. How it comes? Simply this is, let's say, R1, this is, let's say, R2, and this is, let's say, my V in. So my Vx will be how much? V in into R2 by R1 plus R2, and we have to make sure that for highest value of V in, so V in is 12 volt, it is calculated, but it may be possible that V in can go up to 15 volt. Okay, so you have to make sure that up to 15 volt my Vx must not exceed 3 volt, it should be lesser than 3 volt. That's the understanding you should have. Okay, so even if V in max, so basically we have V in minimum and V in maximum. So at V in maximum, it should not be more than 3 volt. So that's the one thing that you have to make sure in the resistor division. Now one more thing, why we are taking 390 kilo ohm and 75 kilo ohm is, since this is a battery, so there will be always a current that will be flowing through these two resistors, right? 390 kilo ohm plus 75 kilo ohm. So total will be how much? V in by total R1 plus R2. That much current will be flowing always, which will be kind of leaking current, or it will be, flowing through this and it will be getting wasted. So I don't want to waste much of the current. That's the reason I have taken higher values. Understood? If it is a supply voltage range, let's say you have some LDOs or something like that, or maybe switching regulators, and that's how you are generating 12 volt, then you can take little bit lower values of resistor also, so that your current becomes, just less than around a milliampere. But at the same time, you make sure whichever power source you have, whether it is 12 volt or 3.3 volt or 5 volt or like 9 volt or 7 volt, any voltage is there, try to keep the resistance division in such a manner that the node voltage comes less than V reference. Okay, and at the same time the current flowing through this resistor should not be less than, should not be around 1 milliamps. Okay, just try to keep lesser than that, so that you are not wasting current here for that. Okay, so that's the one step. So keeping the voltage range lower than the V reference. Next is, we will not even now directly send it to the ADCs. Okay, so first of all, what we will do, as soon as we have connected to the, let us say my Vx value has come less than V reference, which has to be going to the ADC value. Okay, now if it has enough capability, let's say around 1 milliamps current or something is available in that, then simply connect one low pass filter using RC. Okay, so this is my low pass filter using RC. and if it is DC voltage, then you can keep 100 ohm and 0.1 microfarad blindly, okay, and it will be working properly, okay. So how it works is, basically this is low pass filter, and the process will be, my cutoff frequency will be 1 by 2 pi RC. Understood? So let me take you the calculation again. So let us say this is 0.1 kilo ohm, that is 100 ohm, right, and 0.1 microfarad. So the cutoff frequency will be 15 kilohertz, okay. If you increase to 1 kilo ohm, then cutoff frequency will be 1.59 kilohertz. If you increase to 10 kilo ohm, then cutoff frequency will be 0.19 kilohertz, okay. So that's the meaning. Understood? Now we'll just keep here 100 ohm, okay. So 15.9 kilohertz we are taking. Good. So this is the one way, and you can directly send it to the ADC. But the main condition should be the current flowing through the resistors, or the current going into the ADC, must be around 1 milliamps or so, okay. At the same time, what you can do to avoid this particular understanding is, let's say your current is just microampere, like 1 microampere or 2 microampere, so that will not be enough to charge the ADC's like input, okay. So at that time you have to have a buffer. So in that case you can use your input, like your Vx, okay, which is going to ADC as input, that will be going to a buffer. So this is an amplifier which you feed it to the positive terminal of the amplifier, and negative terminal directly connected to the output. So that's called, it is called buffer. So that is non-inverting buffer, okay. Now you send it to again one RC filter, and then send it to ADC. So this is another practice. So this is first practice, this is second practice, okay. So you can have very good amplifiers. If you have a problem of having like a temperature variation of your ADC outputs and something like that, then in that case you can take up some of the op amps which are zero drift op amps, okay, like OPA 2277, or you can take up general op amps if you don't have any issue with your temperature variation. Let us say LM324 or LM358 or something like that, okay. Good. Now one more thing, what happens is, let us say you have a problem of having some like a low pass filter you want to have in the active mode itself, as well as some amplification. So you have the ADC input, and that ADC input will go through the positive terminal, and you have RC combination. So this is kind of integral amplifier, okay, so integrator. So this will act as low pass filter again, and then one more low pass filter is here to make sure that it is going to give you a proper value, and then send it to your ADC converter. Whether this ADC converter input can be a microcontroller ADC, or it can be a separate external ADCs that we have already discussed, okay. Now there are various occasions in medical field or somewhere where you do not want just the low pass filter, okay. Let's say this is my FC, you want something which will cut down my lower cutoff also, okay. You don't want below this signal. So let us say we want this much, okay. So for that you have to have band pass filter. So these band pass filters are basically used in our heart rate monitoring or something like that. So let us say we have some signal that is coming from the heart rate outputs, okay, and that one we have to send it to the ADC for understanding what is my heartbeat, okay. So for that case what will happen, I'll try to take up one LPC, that low pass filter, okay, LPF, low pass filter here. So this is using my RC, okay. Another one, since we have already got how much it is, 1 kilo ohm and 0.1 microfarad, so this is going to be 1.59 kilohertz low pass filter. Now coming back to another band pass filter using the op amp combination, okay. So this op amp combination will make sure to give you band pass filter, okay. So this band pass filter, maybe you can calculate it like 1 by 2 pi RC and something like that. If you do, then you will get around 0.3 hertz to 4.8 hertz. That's the requirement for your ECG heart rate monitoring, okay. So in that case, if you want, you can increase or decrease little bit, like some people prefer 0.5 hertz to, let us say, 6 hertz. So accordingly you can vary your resistors and these resistors. Okay, so this is how you can design a band pass filter. So first step will be low pass filter, then put an buffer, as well as this buffer is acting as a low pass filter also and amplification also. So this is the meaning. Okay, so not just buffer, it can act as a amplifier also, and then you send it to your ADC. So that's the another step. So this can be your third recommended step. So based on the requirement, you can utilize any of the input phase for your ADCs. So what are the places where we utilize ADCs? So as you can see, we have already seen there will be power supply which will be 12 volt, that is from battery, or maybe 18 volt from battery, or 24 volt from battery. So that one you can take it to a voltage division, and that voltage division must be your, let's say, Vx1, which is going to be less than your V reference voltage. If it is from supply rails, then you can try to keep little bit higher, a little bit lower resistance values, so that your current is little lower than around 1 milliampere or something like that. That's the another way. Okay, so there are various occasions you can have voltage ranges up to, let's say, 12 volt, 15 volt, 9 volt, plus minus 9 volt, 7 volt, plus 5 volt, 3.3 volt, 2.5 volt, 1.8 volt, 1.5 volt, 1 volt. So all these voltages are used in like FPGA systems as well. So there are a lot of FPGA systems, and you have lower voltage input supply for uh, let's say pressure sensors or temperature sensors. So for that purpose also you need to keep monitoring all these voltage levels. Now there are negative values also. Okay, so let us say minus 8 volt is there. So what will you do? So in that case also you can go ahead with your voltage division, and then keep your voltage and use a bipolar IC which will be taking your negative values as the input also. At the same time, if you want to utilize your microcontroller ADCs as the monitoring device for this particular voltage level, so what will you do? You can send it to one of the inverting amplifier like negative and positive. So like that you can send it. Okay, and then you send it to your ADC. Okay, so you invert this voltage level and then send it to, and whatever the ADC value that is coming with, that will be coming up as positive value, and then you send it to then you convert it to corresponding to negative value. So how it works, you can do something like this. Let us say minus plus. So keep gain, let's say I am going to keep it like 1 kilo ohm, 1 kilo ohm. You can keep it lower also, and then this will be the voltage input for your negative voltage, and this will be ground. Okay, and in that case whatever V out is going to come, that will be going to your ADC. So this is how you have inverted your input so that it becomes positive, and then send it to your ADCs. Understood? Alright, so these were the some of the occasions. Some more occasions are these days you have lot of temperature sensors outputs. So we have temperature sensor, or we have like NTCs, like negative temperature coefficient sensors. Okay, so there you need to utilize your ADCs, and at the same time we'll see some examples as well. We have some pressure sensors also, where you can take like obsolete output or differential outputs. So that also I am not going to tell you how to design the compensation circuits and amplification circuits, because we will be taking not directly this pressure sensor output. We will be going, let's say this is my pressure sensor, then we will be going through some amplifications. Okay, and then we will be sending it to my ADC value. Understood? So all these conditioning circuit and amplification circuit we have already discussed in our sensor sessions. Okay, so in sensor application session you can understand. Let me give you some of the examples that you can directly take into account. So let us say we have one ambient light sensor that is going to give you some output, which the part number I have used is VEMD 4110X01. Okay, and this is the integrator mode kind of thing. So it is going to give you one low pass filter kind of thing, and this low pass filter is around 6 kilohertz. Okay, now this is acting as a amplifier as well, and then again low pass filter, and then it is going to go to my ambient temperature sense, which is actually one of the ADC pin. Okay, so based on your ADC, whether it is microcontroller ADC or external ADC, you can send it to the input of your ADC converter. So this is one method for your designing ADC converters. Understood? Another, we will take an example of, let's say we have already discussed temperature sensors lot of time. So one temperature sensor is TMP 235. So this TMP 235 gives an output of around 10 millivolt per degree centigrade, 10 millivolt per degree centigrade increase. Okay, so this will be like directly able to send it to ADC value. Okay, so you can send it directly to ADC value, which will be measuring the output. So simply you have to give one voltage to this particular sensor, you have ground pin, and output pin will be directly taking it. Similar to that, we have LM35 also, which is very popular IC. Okay, so LM35, we have taken that example also in our lot of microcontroller sessions, so that one also you can take. Now coming to the fact that, do you think directly sending it will be good, or you can, if you want, you can do one more thing is, instead of directly sending it to ADC, you can again from here, let's say this is my out 1. Okay, and this out 1 will go through, this is my out 1 will go through one of the buffer, then send it to low pass filter, and then send it to ADC. So this is another method to send it to your ADC converter for better understanding or better output position. Okay, good. Let us take one more example. Let us say we have the battery voltage as I told you. So we have here VDD, let's say up to 5 volt it is there. So 5 volt I have converted it to 30 kilo ohm and 20 kilo ohm. So maximum it will come up as 2 volt. Okay, now this 2 volt will be going to the buffer. So this is my buffer, then going to my low pass filter, and this low pass filter you can design it, either you can increase little bit to 1 kilo ohm also, because this is a simple DC signal. So you can keep your low pass filter as close as, let's say, 1.5 kilohertz or something like that. If I am going to keep 100 ohm, then it will be 15.9 kilohertz. Okay, so this is how you will be working. If you increase it to 10 kilo ohm, then what will happen? Let's say I will increase it to 10 kilo ohm resistance value, then it will become 0.15 kilohertz, that is 159 hertz or something like that. Understood? Similar to that, any ADC value that is coming up, you can send it to the buffer and then send it to the low pass filter, and it is going to the ADC converter. So this is how some of the best recommended methods that were there, and we have used some of the ICs that I'll just try to give you those applications. So we have some of the best ICs that we had used in our past applications, like ADS 8860, ADS 8864, ADS 8865. We have ADS 7142-Q1. This was for automotive application. Okay, we have very good ICs from analog devices also, like these were all from Texas Instruments. Okay, so we have from analog devices, one of the best IC that I have recently utilized in our schematic is AD4008. Okay, so AD4008, this is 16-bit ADCs. If you want to, this is going to be 500 kilo samples per second. Okay, if you want to increase the speed, then it can be 1 MSPS, like 1000 kilo samples per second, and this will be 2000 samples per second. Okay, so you can utilize AD 4000, 4004 or 4008. So 4008 we had used because we don't need lot of speed. Similar to that, AD 4000, 4052, then we have Max 11160, we have AD 7686, we have LTC 1860. So all of these ICs we have already used in our applications in lot of like different applications like medical devices, consumer applications, and FPGA systems and something like that. One of the best thing that I observe about analog devices ICs are, if you see this particular data sheet, then you will have a particular table. So this is the particular table that is going to be, and it gives you a very good table having beats, then what is the speed. Okay, so the different speeds are there, and you have 14 bit, 16 bit, 18 bits, 20 bits precision SAR ADC. Okay, successive approximation resistor ADCs, right? So you can see we have 20 bits ADCs, so you can see directly the part numbers, which is going to be 400 kSPS to 500 kSPS, which is AD 4022. okay, or AD4022. Similar to that, whichever application you need, let us say I need a 16-bit ADCs, then you can go directly ahead with AD7684 or AD7687 for 250 ksp's, or if you want to increase the speed, then you can go ahead with AD7688, okay, or AD4011, okay, or 4001. Similar to that, 16-bit other ones are there, and then we have 14-bit. So any of these ICs you can utilize for your particular applications. So hope you guys have understood what are the best approaches or best practices that we follow for the ADC applications, or how do we process our voltage labels before sending it to the ADC input of your microcontroller ADC converter or your external ADC converters. And there are a lot of ADCs that we have already seen in our sessions. What are the processes of ADCs, how it converts to the ADC values, that we will not talk about here. So if you have any questions regarding the any connections towards the ADC inputs, please put down your questions in the comment box and we shall be able to answer you out. Thank you.